All right, so we're going to pick up with electrolytic cells, yay? So you could have an electrolytic cell that looks like a galvanic cell but instead a battery connected to it. We did one like that instead of not a battery. But the one we did in class, we would hook it up like this. And so kind of looks similar to the galvanic to start with. This is what we call electrolysis. The biggest difference here is you have to have a battery. So this is electrolytic. So, English. Couple things to think about. Electrolytic cells, by definition, are not spontaneous. So my delta G has to be positive. And in this instance, you're storing energy or using energy during this reaction. So your E value is going to be negative. So typically when we set this up, you're going to use two metals here that themselves are not reactive. So the metals, when you connect them to each other, are not going to be the ones transferring energy. We're not going to be transferring electrons. It's leaving the battery to make that decision. So now we're going to flip on this battery, and it starts the flow of electrons. So right now, everything's neutral, but we can start a battery up, and we can just decide which way we want those electrons to transfer. And so now we have dictated which way those electrons are going. Well, the battery has. And so because this was originally neutral and we're forcing those electrons to that side, now it's going to get a buildup of negatives, but it's still gaining the electrons, so it's still the cathode.
So this is the negative side of the battery and this positive side, correct?
Sure. I don't know what this.
So
It's hard to watch your fingers. The brain's tired. All right, so then this side's going to be positive because it's pulling the electrons out. It's forcing them out. And this is going to be the anode side, though, still because it's losing. So that's one of the biggest differences between galvanic and electrolytic, is the charge of the metal there. But your cathode is always gaining and your anode is always losing. So cathode is still reduction and anode is still oxidation. So far, so good. But remember, in a setup like this, electrons can't just travel on their own. They will not complete this circuit unless, because if this is just water, water doesn't have the charge available to transfer electrons through it. It has to have ionized water. So that's why you would put in some sort of ion into this reaction. Put in Ki. So we'll have K positive. Okay, here, let's talk about this, because I've had a lot of people do this to me. So Ki here is a solid, right? Ki as itself does not have a charge. But the K in there still is charged, and the I is still charged. But because they're bonded together, they neutralize themselves. But they still both have a charge. So when they go from being K like that, now it's going to become K positive, I minus. It's really still the same thing as what it was before. We've just increased the surface area. Before they were bonded together, now we've separated them. It allows your reaction to happen more effectively because we know rates of reaction that allows for better collisions. Yes, sir.
Does that also increase entropy in your dissolves?
Mm-hmm. Any other questions? Okay. So then, as now the electrons are able to flow, this is going to become more positive. This becomes more negative, and so it attracts the appropriate ions. This positive ion gets pulled towards the negative, and the negative ion gets pulled towards the positive, because opposites attract. And now, to continue the flow, continue the movement of electrons, one of these ions that is hanging out over here, either the K plus or the H2O, will actually continue gathering those electrons so it can keep moving around. So one of those is going to pick up the electrons. And on this side, I minus or H2O, one of those will be giving away their electrons. So we need to learn some information about those to figure out which one will do it. So that's where our reduction potential chart comes into play. So you'd probably be given these 4 different reduction potentials and have to decide. So the cathode side, I'm looking for K plus reducing. Oh, shoot. I don't have on here. I'm just going to switch it to CD because I do have it on here. So we'll pretend like this was CD. Okay. What's wrong? You're mad because I changed it?
Okay,
Well-
it's on the very bottom. The second.
Of the second page.
I don't have my second page. I only have the first one. If you have it, you can read it to me.
I'll just give it to you, so it's-
Okay, well, I don't care. You guys were the ones who were mad at me. What do you want it to be? You want me to leave it? Oh my gosh, you guys are silly.
So you want this or no?
No, apparently I'm not allowed to change it again. Let's just pick a different one. Let's change it to another one just for fun. Jokes. Just wanted to make you guys mad. You could have told me that it was bothering you. All right, and then we're looking at waters. This is on the second sheet too. I think. Do you want to read that to me? Joey, can I have that sheet back?
It says the K on it.
Okay, well, I can't. I need the water.
Oh, you take it.
I think it's on this one. Oh, you got this one. You don't have the second sheet either.
What are you talking about?
I am not very good at auditory hearing, so it would be hard for you guys to shout it all out. So auditory, not like I can't. You guys know. Show me the Okay.
See sound.
I'm gonna stop helping you people. Okay. Literally reteaching you the unit and you are mocking me. That's what's happening right now.
How do you know which pH
Thank you.
water value to use?
What a great question. So the reason why I picked this water equation instead of the other one that I had, negative 0.828.
On our sheet, it just says negative 0.83.
If I change it, they'll probably quit. Which might be okay for everybody. I don't know. So I picked this water equation because here water is coming together with electrons, and we're talking about reduction. So I need water to be gaining the electrons. So that's where we talked about them being on the same side of the equation. So I have to pick this water equation as opposed to the other water equation where water and electrons are separate. Yes, David?
There's another water equation that has water and electrons put together on our sheet.
Okay. Where is it?
It's on the first page,
Okay.
probably like 2/3 of the way down-ish.
Does it also start with oxygen?
Yes.
So the difference here is I only have water and electrons coming together
Okay.
as my reactant because here I don't also have oxygen in the equation,
Okay.
you know?
Yeah.
I would guess that if they wanted you to have that one, they would have given you that one specific. And remember that we're talking about we would have started with only 4 choices as opposed to 100 or whatever this is.
Okay.
Kelsey?
So the end goal of almost rewriting to tell us that H2O.
We're trying to decide which one of these is more likely to be reduced.
Okay, yeah.
Okay, and so remember reduction, which one is more likely to be reduced? How do we decide that? More positive of the bunch. So which of these is more likely to be reduced here? cadmium. So this one's actually going to be the one that gains the electrons, and water's not going to do anything. It's just going to hang out. Connor?
If water were more likely to be reduced, then would we need cadmium?
Yes, because you still need the ions to transfer the electrons. Did you guys still get your question? Okay. So then we're going to do the same thing again. Hopefully iodine's on my chart, because otherwise, sorry, I ran out of space. So here, notice my I minus and my 2 electrons are on opposite sides of each other. Once again, that's really important to show that the I minus is coming apart from the electron. Remember, it's the anode side, so we're going to flip our reaction here in a minute. So just prepare yourself. We're going to have to change it again. And now we want to use the water equation where water is opposite from electrons.
Does it matter what the electrodes are made of?
Not terribly. You don't want to choose electrodes that are really reactive because that can mess with your electron flow, but otherwise not really. We'll typically use platinum or gold or something like that. Did you guys get your stuff figured out?
Yeah, why are water and the electrons on opposite sides?
Because here we are oxidizing, so water needs to lose the electrons. So water and electrons have to come apart from each other.
Is water always going to do the same thing as the anode with the cell too?
I'm not totally sure I understand your question.
So, like, in this equation, I, like the I2, I guess the I is getting oxidized. And we took the water equation that was having water get oxidized. So is that like a common thing?
Yeah, because this is the anode, so that's where oxidation occurs.
Okay.
So that's why we picked that one. And so then when we're talking about oxidation, how do we determine what's the most likely to oxidize? Yeah, the one that's more negative, in this instance, less positive. So which one would that be? Iodide. So we're going to get rid of this. Water does nothing in this reaction. Did you figure it out?
Yeah, I think so.
Okay. So far so good. Because just like in galvanic, this is my anode reaction, you want to show it as actually losing electrons. Right now it looks like it's gaining electrons. So we flip the reaction around to show that I minus is the one that is losing the electrons and turning into I2. And so that causes me to flip the sign from 0.53. Oh yeah, sorry. I must have just not carried that over. I want to make sure it wasn't written wrong on here. Yes.
Okay, I'm still not totally on board with cadmium. How is it helping the transfer of electrons?
Because it itself has a charge to it, so you need a charged solution to move electrons through. So I have to have a positive ions in solution attract electrons and allow for movement of electrical current.
So we've got like electrons moving from the cathode to like cadmium, and then moving across there to the anode.
So the electrons here are going this way and being, in this instance, attracted to cadmium because it's gaining the electrons. That's true.
Right.
And then if you think of it like a flow of energy, right, is able to move. And it can't do that if there's nothing that can transfer electrons within the solution.
So then, like, is the cadmium going and transferring it to the other side?
The iodine is.
Okay. So then the cadmium is transferring from the anode to the cathode?
The cadmium or the iodine? Which one? cadmium is getting the electrons from the cathode. The iodine's giving its electrodes to the electrons to the anode. Okay, keep working on that. I'm going to combine these two electrons here. Two equations. I know I'm getting to the place where you guys can't see it, but I only have such a big board. And so because I've already got 2 electrons on each, then we're good. I don't need to double or change anything. And I already flipped my equation. And then just like on the other equation, we're going to add these together. So what do I get when I add these together? Oh. No? Not interested in helping me? Still trying to see it. Sorry. I just added the 2 equations that you guys have on your paper. You could do it yourself.
You took my paper stuff.
Oh, I'm sorry. I think I'm done with it. You can have it back. I appreciate you having it handy. I think that's it. Yes, Dave.
Alright, so I'm still confused, like, what is the role of water? Like, why do we have to compare, like, the element, like, the ions, or I guess the reductions of the anodes, like the metals to water?
Okay, I think I get where we're coming from here. Okay, so we can't just put ions next to the metal because they have to be dissolved in the water, right?
Yeah.
I guess, I mean, it would be hard to just like, you couldn't have a completed circuit if you just put them in 2 different containers of solid cadmium iodide, right? So we dissolve it in water. So now we have a solution just that naturally has water, iodine, and cadmium in it. And the cadmium and the iodine in this instance are what are providing the ability for electrons to actually be able to have a complete circuit. So somebody's giving up electrons and somebody else is gaining electrons. And we have that ability, whether it's water, whether it's electrons, it has to get started at some place. So you have to consider the fact that both of those are there and that water and cadmium have equal opportunity to gain electrons. And in some instances, water is the one that's more likely to be reduced. In this instance, it happens to be cadmium. But in class, the one we did last time, water was the one that was more likely to be reduced. So you have to take a second to think about both of them. You can't just assume that the metal will be the one to grab it. Does that make sense?
So, I guess my other question would be, why do we assume that in the solution in the galvanic cell, that water, like, doesn't have the opportunity?
Because in the galvanic cell, the ones that are doing the reacting are the 2 metals that are hooked up. So they're the ones that dictate the flow of electrons. And so they're going to become or form or whatever, gather the ions that are the respective metals.
Okay.
So
Hunter?
if water were the one being reduced,
Mhm.
would it be transferring electrons, turning into other stuff?
Can be turned into oxygen and hydrogen and
Would we get like bubbles of?
yes, you would.
Okay, so when you're looking at the oxidation one that's more negative, you want to always look at the beginning, the reduction values, and not flip it and then flip the signs to the other.
Right. Because then if you flip the signs, now you're looking for the one that has the more positive sign. So it gets confusing. So don't do that.
Okay.
So where does the solid iodide go?
Well, iodide is a gas. No, it would gather on the cathode or on the anode, excuse me. We just like collect on the outside of it. Except here, the cadmium would be turning into. Oh yeah, no, you're right. It would gather. I'm galvanic mixed up for a second. Lauren?
On an iodine snap reaction, should you flip it before you compare it to water?
No,
Never?
flip it on the reduction. That's the way that our rule, like, then that way everything's consistent. And it,
Oh, is that because you'd be comparing the oxidation reaction to, okay.
well, yes. So then you'd have to flip both of them. And then you would want to be looking for the one that's bigger of the numbers because it's more likely to oxidize. And I just find that to be confusing for people. If you always like galvanic, you always use the same pattern, you kind of used to it, go with it. Eunice, did you have a question?
This is more like galvanic cells, but like the cell potential increases when the cathode concentration increases, right? Because the cathode is a reactant.
Right, because think about the solution that would be on the reactant side. When you have excess of that, it's more available to collide with the metal and grab those electrons, and so it flows the electrons more quickly.
So it's the ions in the solution.
Correct. Yeah, because we're talking about the concentration of the solution.
So that would cause the forward reaction to move more quickly.
Correct. And then conversely, the anode being greater causes it to move more slowly because you've already colliding a lot with the metal and it's more difficult to create those ions. Yeah, we started talking about galvanic. Yes, that was all for galvanic. Okay, I think that I'm done with this. Do you have questions about that? Do you want to stop because you guys don't have like a ton of time? You have 25 minutes left of class, right? And then stoic calculations and redox is what we have left. We can finish this and record it, everything, or we can stop and give you guys time to work. How many people want to keep going? How many people want to stop and work? Okay, well, you guys can stop and work, but you got beat too. Most people didn't care. All right, do you have a problem that you want me to work out that's stoichiometry and coulombs and all that good stuff?
I know there's one on the practice.
Okay. What are you not getting why about?
What?
Do you have a question?
I was just still confused on
I
like
just
where the electrons go, like, so they react with the cadmium and the iodide, but I don't get the,
So iodine's giving them up and cadmium's getting them.
and then it just goes back again, keeps going.
Because there's a ton of iodines. Remember, it's not just like one iodine in solution. So all the iodines, as they run into the surface, they will give up an electron. And then on this side, as the cadmiums run into the surface, they'll grab the electrons.
And it'll never end.
It will eventually
Battery
end.
is still going?
No, it'll eventually end if your battery dies or if you run out of iodine ions or cadmium ions in solution in this.
So once they react, once those ions react once, then they can't.
Right.
Is the battery sending electrons to cadmium and those are transferred from the solution to iodine? Or is it taking electrons from iodine and giving it
So
to, like originally at the very beginning?
it starts with the battery pulling electrons from the metal that didn't have a charge to it. It pulled the electrons out. And then because now this was missing electrons, the iodine, because we figured out it's so more likely to be oxidized, then started to replace those electrons by adding them to the metal
From the solution.
from the solution. And then this side now has become negatively charged, grabs those cadmium, and then cadmium starts picking up the extra electrons. Does that make sense?
Oh, and so then
Because then the,
going onto the metal.
Yeah.
Is it possible that the solution run out of ions?
yes, and then they'll stop.
I
It's
thought
like
the
reached
battery-
equilibrium.
So it's both the iron
Just
battery
wanna-
gets-
Do you want to stop? Because I'm fine. I said we could
Oh,
stop.
no, we have to leave early.
Okay, what time do you have to leave?
2:40.
All right, which one do you care about, redox or galvanic calculations more?
So is it whatever reaches equilibrium?
Stoic? Okay, Kirsten has a problem for me.
Oh.
Did you want me to do the one off the FRQ? Is that what I remembered you saying?
I had a read off.
Oh, Lauren, I'm sorry. I knew it was somebody from you at your table. I'm so sorry. Do you have the thing you want me to say? Nickel. So we had 40 minutes and we have 1.5 amps. And then we want to know how many grams of nickel we can plate or something in that amount of time. Go for it.
In the electrolytic cells, does it
Could do it either way.
equilibrium when it comes out of ions?
Yes,
Is that considered equilibrium?
That can be considered equilibrium. Okay, so I don't remember if this one was galvanic or not. I don't remember how it was worded, but these are going to be the same either way. You'll do the same process, same idea. So that shouldn't impact your results. So remember that amps are going to be the same thing as coulombs per second. So if you have 1.5 amps, you have 1.5 coulombs in 1 second. So you cannot start, well, you don't typically start stoichiometry with a conversion. You would use that within a setup. So I'm going to start with the 40 minutes. The question is how many grams of nickel? And so if we start with 40 minutes, I need to get to seconds so I can use my number of amps. And I know that in 1 minute, there are 60 seconds. Because I just did the amps, I figured out that there are 1.5 coulombs for every 1 second. So now my seconds have canceled, my minutes have canceled, and I'm left with coulombs. I'm going to take a break because there's a lot of writing happening. Thank you. Okay, so now I need to go on, and I need coulombs to be on the bottom. What do we know about coulombs? 96,485. Because this is an FRQ, I'm going to go ahead and use the exact number from the FRQ sheet. It's on there. You can write it down, but you want to be more exact on the FRQ. Multiple choice, I would just round it. And remember, that's for every mole of electron.
What will we round it to?
It just depends on like what you're calculating. Something that makes your math easy. So then I canceled my coulombs. And now I'm at moles of electrons. So I want to know how many moles of electrons are related to 1 mole of nickel. Or I can't remember if it's gaining or lost from a mole of the nickel. And this is going to be 2 electrons because it's an Ni plus 2. So I'm going to put 2 moles of electrons down here at the bottom. And then lastly, I need to get to grams. So I'm going to go from 1 mole of nickel to the mass of nickel. Once again, since it's FRQ, we want to be as close as we can. I think it's 58.6. Sound right?
58.7 if you round it there.
Okay, so what would be 6 what?
58.69.
58.69 grams of nickel. So that allowed my moles of nickel to cancel. So now we would multiply and divide accordingly. And I got 1.10 grams of nickel.
How did you get 3 figures?
There's 3 significant figures here. And I think this was 1.50, if I remember correctly.
So are grams on the ending okay, or do you want us to 58.6?
No, you can just leave this as what it is on the periodic table.
Okay, so it doesn't.
Right. In fact, the more numbers you have there, the better. Yes.
So if, like, let's just say we had they gave us an element, but they didn't tell us the charge of that element, and it had multiple charges that we could pick, like Fe. Which one would we pick?
They wouldn't do that. Because in this situation, you're going to be looking at like a galvanic cell or an electrolytic cell where you've either found the reduction potential half equation or they gave you the half reaction. So in order to be doing this problem, you would be basing it on a half reaction, which would have told you the number of electrons.
Okay.
Like if it said, the only thing that would maybe come up would be like, let's say I had a solution of NiNO3 2, like this. You might be told in this way what the charge is of nickel.
That's true.
So here's a way of letting you know what nickel's charge is. And so they might say it that way. Okay? Sounds good? I feel like this is probably a good place to stop because you guys seem like we've checked out. I can happily do redox if you guys want me to, but I think a lot of people are really tired of listening to me talk. Is that a fair assessment? How many people want me to do the redox problem? How many people don't?
People don't care.
It's not going to hurt my feelings. All right, we'll do redox. I don't care if you don't listen to me. By all means, work and do something else. Okay.
I'm 11 on that redox. but sulfur dioxide gas will bubble through a acidified solution of potassium permanganate.
Okay, so SO2. Yeah, hey.
Do we need to explain the last one or just say?
Nope, just predict the sign.
All right,
It's
thank
only
you.
a 4-point problem. So then, where's my sheet? Here we go. This sheet right here is where I'm going to look for some information. I know this is an acidic reaction. I see permanganate. We know MnO4 in an acid typically becomes Mn plus 2. So I need to look down here for something SO2 is likely to do. And it looks like to me that SO2 is likely to become SO4. So that's how I predict my products just right off the start. Then I'm going to split my reaction in half. I'm going to get rid of my K because I don't care about it. Switch it to SO4 2 minus and MnO4 minus Mn plus 2. Okay, and then I'm going to balance each half reaction in terms of atoms and then electrons. So in this half reaction, I've got 2 oxygens on the left and 4 oxygens on the right. So in order to balance it, I need 2 more on the right. So we would add 2 water molecules because each water has an oxygen in it. I know they're available in the solution to be able to react with. But when I do that, it gives me some hydrogens. And so now I've got an addition of 4 hydrogens. Questions on anything I did there? And so now that our atoms are balanced, we want to make sure, because my sulfurs are balanced, my oxygens, everything's good. So I want to make sure that my electrons are balanced. So on this side, I've got no charge and no charge. So here I've got 0. And here I've got a -2. And I have 4 positives. So overall, I've got a +2. So what do I need to do to get that to be 0, just like the other side? I'm going to add 2 electrons. So now that half reaction is balanced. I have to balance my second half reaction using the same steps. Since I have 4 oxygens here, I'm going to put 4 waters here, which then gives me 8 hydrogens here. So far, so good. Okay. So on this side, I have 8 positives minus 1 negative. So that gives me +7. On this side, I have a +2, and then that's no charge. So it's just a +2. So what do I need to do to make the 2 sides equal? So now that my 2 half reactions are each individually balanced, I need to start putting them together. And so I need to make my electrons match. So on the top, I've got 2 electrons that are being lost. And then down here, I have 2 electrons that are being gained. Obviously, that's an issue. So we're going to double this bottom reaction and multiply this top one by 5. So this becomes 10 electrons. This becomes 16 hydrogens. 2 MnO4s, 2 Mns, 8 waters. Then up here, when I do this, this becomes 10 waters, 5 SO2, 5 SO4, 20 H pluses, and 10 electrons. Bye, gentlemen.
Yeah.
So then my 2 electrons cancel. Super duper. And since my electrons are already canceled, I want to also cancel my hydrogens. 16 H pluses would cancel with my 20 H pluses and leave me with 4. And then my waters here can cancel with these 10 waters and leave me 2. And since that's all that I can cancel out, I'm now going to add everything together. this moment, it's an acidic reaction, so I don't have to do anything else. If it were a basic reaction, now because I have 4 H pluses, I would need to add OHs to both sides, combine them to be water, and then once again cancel out waters. That's not what's happening. So I'm going to now just double check my charges and make sure they're all right. So there's 2 times 0 plus 0 plus 2 negatives. So overall I've got a -2 on that side. Here's -10 because I have 5 -2s plus 2 +4s, or +2s gives me +4, and then plus 4 more. So that gives me -2. Success. Since my negatives cancel, that's a really great way to check your work, that, or my 2 sides are the same charge. That's a great way to check your work. Yes, sir.
Could you finish it like it was?
Sure. Okay, so this is what the right answer would be, assuming it's an acidic solution. We're going to change it and say, just kidding, it's for basic. So probably the permanganate that would have happened up there would have been different anyway, but let's just pretend like it wasn't. So on this side, I'm going to add 4 OH minuses. And if I do that to one side, I have to do it to the other. And so these 4 OH minuses become 4 H2Os. Are you finished? Thank you so much. Do you mind if I keep on?
Yes.
Okay, and so then I have 4 H2Os on the right and 2 H2Os on the left. So those are going to cancel and become just 2 H2Os overall. And now I'll just bring everything back down. So now my final equation would have OH in it, since it's in a basic solution. It would still be a good idea to double check your charges. So you got 4 negatives plus no charge plus 2 negatives. So now I'm -8. So far so good. And over here I have -10 plus 4 -6. Did I do my math wrong somewhere?
The left side should be negative.
What did I do wrong?
You added them.
Oh, because -2. Wow. Whew. Thanks, guys. I don't know how I did that. All right. What can I do to help you? Anything else?
I have a question on some of like the practice FRQs. A lot of them are asking about like what happens to like cell potential if like the concentration changes. I guess I don't know.
So earlier when we were talking about, we kind of talked about that a little bit with our galvanic cells. Because that's when that would come up, is with the galvanic cell. And that's when we were talking about like the cathode having the greater concentration or the anode having the greater concentration. So it's always going to be your cathode solution plus your anode metal will always then turn into, in whatever order, your cathode metal and anode solution. So like in a like any cell, that's going to be the general idea, right? And so if we increase the concentration here, we're adding the amount of ions that are available to react. And so if this is the higher concentration, it's going to collide with the metal more often and be able to gather electrons more quickly. So if this is increased, you get more collisions, which means faster electron flow, which means higher voltage. Now, if my anode solution is higher, if this has the higher concentration, we already have excess of your positives. Essentially, having too many positives makes it difficult to make more positives. So it slows your electron flow, decreasing your voltage. So remember, it's the ratio between your two solutions. Yeah. So this would be the instance when this one's higher. This would be if this one's higher. They can't both be higher. Seems like a really great place to stop. I'm gonna stop this now. Thank you guys. I appreciate it.